at quantum algorithms. So the first idea I would like to share with you is that quantum information is rather special. It has a certain special property that it cannot be copied. So you cannot have a photocopy machine which takes one piece of quantum information and puts it onto another piece of it, onto another, say, object. This is a famous theorem which is called the no-cloning theorem. What the no-cloning theorem means is that if you had a quantum state psi and you wanted to copy this state, which means you want to create another particle that possesses the same quantum state, it's impossible to do that. You cannot copy quantum information. A state, quantum state, cannot be copied. Which means that if you had another qubit or object sitting with this, and this were in an arbitrary state, say 0, and there is a state psi that you would like to copy onto this placeholder, it's not possible to do that. So this process, psi tensor with psi, is impossible. You cannot create a copy of psi. So this is not allowed. That is the no-cloning theorem. Now, the no-cloning theorem is closely associated with our inability to measure states. If we had the ability to measure a quantum state, suppose we gain some kind of supernatural power and we are able to measure the state psi precisely. Then if we were to measure the state psi, we would be able to do a transformation on this initial state and make it into psi. Right? So if you talk about qubits, every qubit lives on a Bloch sphere, and the state psi lives on a certain point on the surface of this Bloch sphere. So if you are able to measure the angles theta and phi for this quantum state, that means you are able to determine what the state is or measure what the state is precisely in one go. And if you are able to do that, you take then another system which is in some other quantum state, say psi, and do a transformation that converts this psi to, that converts this 0 to psi. So no cloning is tied up with our inability to measure states. Since we cannot measure states precisely in one go, arbitrary quantum states in one go, it's not possible to clone quantum information or clone quantum states. You get this point? So let me also prove the no-cloning theorem. Let's first of all mathematically see how this theorem is proven. It's a very simple proof, by the way. Suppose I have a quantum state psi, which is, I'm talking about a qubit. An arbitrary state of a qubit could be, say, alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers, right? And alpha mod square plus beta mod square is 1. So it's a normalized quantum state. And what you would like to do is copy this state into another state. And copying means you preserve the original as well. That's what copying really is. So cloning means that you have an unknown, arbitrary, totally arbitrary quantum state and you have a scratch qubit or a rough qubit which is in some state, say ket 0. Let's call that state ket 0. And the proposition is that there is some unitary transformation, say UC, a cloning unitary transformation, a hypothetical, purported or proposed unitary transformation that clones this quantum state into this scratch qubit. So this is the first qubit and here is the second qubit. I might drop this tensor product notation because, as I explained earlier, it's superfluous. So this is the cloning operation. Alright? Now I want to show you that such a unitary transformation does not exist. This kind of U does not exist, G.
Just a question about like in the last class if you have two qubits entering into a gate and then escape from inverse apply करते हैं after तो वापस restate आ जाती है जो पहले थी तो isn't that copying for example if you begin with a state मतलब a qubit की state 1 and the second one 0 and you feed it into a quantum gate and then apply the inverse of that and you will get the same state that you started with.
So what I think, let me write a diagram for this. I'm proposing that a cloning operation exists which takes in two qubits. One is in the state psi, the other is in an arbitrary state, let's call it 0, ket 0. And if cloning were to exist, and if it were possible, then cloning means that nothing happens to the original qubit. And this qubit also takes the form psi. This is cloning. This is hypothetical cloning. What the theorem states is that this operation is not possible. This operation, however, is possible. I take up psi, I take some other arbitrary qubit, arbitrary state phi, and the question is whether this operation is possible. This is not cloning, this is swapping. So my current subject of interest is whether this operation is possible or not. Alright, so now I'm going to, so in other words, mathematically I want to see whether such a unitary operation exists or does it not exist, G.
Is it possible that when we like 0 remains 0 and psi remains psi, like both states remain psi?
That's very much possible. That's an identity operation. Do nothing on it. If you do nothing on this, psi remains psi, ket 0 remains ket 0.
So why we are trying to say that if psi को भी वापस से दूसरी state में psi को बनाना?
Because we want to determine whether cloning is possible or not. Cloning means we want to copy this arbitrary state psi. We want to see whether this thing is possible or not. So an arbitrary quantum state psi, its general form is this thing. We want to see whether we can copy this information onto another qubit or not. So what's the problem with this? क्या मतलब क्लोनिंग का क्या मतलब होता है? हम इस स्टेट को कॉपी करना चाह रहे हैं। ये कॉपी नहीं हो रही. This is just original qubit, right? This is just the original qubit. Copy means you want to make a copy. You start off with one quantum state psi and you want to get two copies of it. So cloning is really nice. If you were to clone quantum states, then it will be very easy to initialize your quantum computers because you start off with one qubit and then keep on getting copies of it. But that's not possible. So that's what I'm going to prove right now. So copying really means, copying doesn't mean that you destroy yourself and appear somewhere else. Copy means you preserve your own entity and create another image of yourself on another object. That's what cloning means. It's like creating a twin of yourself. Creating a twin does not kill oneself, it just creates another copy of you, another version of G.
So for example, if we have both initial states are vacuum state, and we convert those vacuum state into ket psi, for example, and is that also lies under cloning? I mean,
No.
is that different?
Ket 0 going into ket psi is not cloning.
So both have ket 0, and when they enter, both become ket psi.
Well, that is possible, but that's not cloning. So any vacuum state or ket 0 can be converted into psi with a unitary transformation. Cloning means you have a state. I think it's really simple. You have a state psi, and you just want to create a copy of it. Really simple. So I would like to argue that this is not possible. Now suppose such a unitary transformation exists. Now if I were to write my initial state before the proposed cloning operation as psi ket 0, after cloning this will become psi ket psi, correct? And I can now break this psi into its component form alpha ket 0 plus beta ket 1 tensored with alpha ket 0 plus beta ket 1. Correct? So I'm just writing down the expansion of each ket in the basis ket 0, ket 1. This equals alpha square ket 0 0 plus alpha beta ket 0 1 plus alpha beta 1 0 plus beta square ket 1 1. Correct? Now suppose I just expand psi right before the cloning operation into its basis states. So I do this manipulation. I put in the decomposition of psi right here before the cloning operation is implemented. Alright, so this means alpha this is what this means. So this is just another way of writing the initial state. Now I would like to implement the proposed cloning operation onto this initial state. I'm just looking at the same evolution from two different approaches. And I'm using the linearity of unitary operators, the linearity of quantum mechanics to arrive at what this state is going to evolve to under a cloning operation. Now if I apply the unitary operation corresponding to cloning here, what would I get? This ket 0 is cloned, so it gets cloned to the same state alpha 0 0 plus beta 1 1. Is this state the same as this state? Or are they distinct states, different states? They're absolutely different states. Therefore, such a unitary transformation does not exist. If quantum mechanics is linear, which it really is, and if unitary operations are linear, then cloning cannot be true. Cloning is not possible. It's only possible, only possible when either alpha is 0 or beta is 0. So you can come up with a unitary transformation that does this. Say some unitary transformation U1 that clones this ket 0 onto a scratch qubit and clones ket 1 onto the scratch qubit. So the same unitary operation can clone orthogonal states, ket 0 and ket 1. But you cannot come up with a unitary operation that takes any input state, any arbitrary input quantum state, and clone it. It can only work in the cases when you know that the input states are mutually orthogonal. You can design a unitary operation that takes those basis states and converts it into the clones. In other words, another way of looking at this is that you cannot perform a measurement that distinguishes between two non-orthogonal states. You can perform a measurement that distinguishes between ket 0 and ket 1. So if I were to talk about my archetypal beam splitter, it takes a quantum state psi, and there are two output channels, ket 0 and ket 1. If I knew that my input state were either ket 0 or ket 1, then it's well nigh possible that I can determine by looking at the detected clicks what the input state is. Because if it were ket 0, this detector is going to click 100% of the times. Just a minute. If I knew that I'm going to input ket 0, so if I'm given the oracle or the question, or I'm given the fact that my input state is ket 0 or ket 1, in one shot, in one measurement, I can determine whether it is ket 0 or ket 1, because I have these two detectors and any one of them is going to click at a time. And if this detector clicks, I can provide an answer to the binary question that my input is ket 0. And if this detector clicks, I can provide the answer to the binary question that my input is ket 1. However, if this were an arbitrary input state, alpha ket 0 plus beta ket 1, in one shot, I will never be able to tell what the quantum state is, which means I will never be able to measure the quantum state. Measuring the quantum state means really to determine the coefficients alpha and beta. That's what measurement entails. I'm not able to do that in a single shot. So no cloning is related to the impossibility of discriminating between non-orthogonal states. Just a minute. Let me write this down. I cannot clone quantum information or quantum states. And this is linked up with the fact that I cannot discriminate between two non-orthogonal states with 100% accuracy. So these are two different versions or flavors of the no cloning theorem, or the impossibility of non-orthogonal state determination. Now questions, I can take questions. Yes, Bruno. If I were, alright, so let me give you an example. If my input state could take up two possibilities, and this is, so someone is preparing the quantum states and giving this as an input to this beam splitter, and the preparer, the chef of the quantum state, is telling us that I'm only going to prepare two kinds of states. One is ket 0, and the other is 1 over under root 2 ket 0 plus ket 1. So the preparer is telling the measurer that I'm going to give you one of these states, either of these states, and you have to tell me in one go whether I prepared this state or I prepared this state. In one experiment, just in one shot, in one go, with the measurer, be able to tell the audience and the arbiters of this game that the preparer has given me this state with 100% certainty or this state with 100% certainty. It's not possible because these two states are non-orthogonal. Correct? They're not non-orthogonal. So that's what this statement means. In order to determine whether I'm given this state or this state, I have to repeat the experiment a large number of times, and the preparer has to stick to his original recipe of giving in just one state. He cannot randomly choose between the two preparations. G.
So we can say about the orthogonal states that the loss of information on the measurement is made due to their orthogonality is same.
So loss of information is not due to their orthogonality.
Because when we say you cannot perform a measurement that distinguishes between two orthogonal states.
Non-orthogonal states.
But orthogonal states को क्लोन कर सकते हैं.
हाँ बिल्कुल orthogonal states. So if your inputs are just two orthogonal states, you can design a unitary operation that clones those states. Yes.
So उनका loss of information equal होगा.
Loss of information का क्या मतलब?
When you make a measurement of a state and make a measurement of your orthogonal state.
I'm not making a measurement here. So this is not a measurement. This is before a measurement. I'm just copying the quantum information. This everything is before a measurement. I'm not making a measurement at this point. So cloning precedes measurement. Cloning happens with or without measurement. यहाँ पे मैं कहाँ measurement कर? I'm not making a measurement here. I'm not collapsing the state. I'm just trying to see whether there is a unitary transformation that can take an arbitrary quantum state and make a copy of it.
How can we design a constitution that will get out exactly?
Right. So at the end you have to make a measurement at the very end. But so far this theorem, everything is working without a measurement.
That's the mark.
So so when you want to discriminate, you're making a measurement. Here you're not making any measurement. All right? Yes.
So what kind of approximation is that where zeros will be directed at
This one? So you can write a unitary matrix for this. Can we give this as a homework, please? Write a unitary matrix for this that does this. All right. Let's see. Yes.
Why do we have to work with arbitrary quantities? Why can't we always be
So if you want to do universal quantum computation, which means that something that works with any input state. So when you are building a quantum gate or a transformation, it is independent of what input state you feed it in with. If you're working in a subspace in which you knew what the input states are going to be, and you are ignoring the other states, then it's fine. You can just design a unitary transformation that just takes those input states and gives you the desired output. But generally, if you want universal quantum gates, then you need to make it work for any arbitrary input state. But if you want to prove a theorem no cloning, it must work for an arbitrary quantum state that you would like to clone. Alright? So now let's come up armed with this kind of basic theorem. Let's come up with an algorithm, and this algorithm is the first algorithm that I'm going to show you is rather non-standard in the sense that this is not the first algorithm that generally students are exposed to, but I'm giving you an algorithm that is interesting and is very motivational. And that is the algorithm for quantum teleportation. Now in quantum teleportation, the idea is to take an arbitrary quantum state psi at some location. Yes, please. An algorithm is a formula which performs a specific task or answers a certain question. So what is a computer algorithm? A computer algorithm provides an answer to a question. Quantum algorithm also provides an answer to a question. So you frame your question in a particular manner and you design an algorithm or a recipe or a formula or a quantum circuit or a concatenation of logic gates, and you construct it in such a way that you are able to determine an answer to the question that was posed in the first place. So it is our attempt to respond to an inquiry, to a question, to an interrogation. That's what an algorithm is. So in quantum teleportation is an algorithm that does something really simple. It takes a quantum state psi at one location, let's call it the location of Alice, and somehow transmits this quantum state at another location, psi, which is in the possession of Bob, who can be spatially separated. And the point is that Alice has a quantum state psi. So one possibility is that we measure this quantum state psi at Alice's location and tell the result to Bob. And the Bob has some initial qubit and he does a transformation and gets that state psi. But the problem is that you cannot measure psi. So how will you be able to do that in one shot? Can't do that. So we have to come up with an algorithm that transmits this quantum state. And transmits is a kind of strange word here. That's why the new word is quantum teleportation, which really has a special meaning. So let's first look at the algorithm that achieves this endeavor. So the question is, what we want to ask is, or the task that is at our hand is, we would like to transmit this quantum information. Psi, this state has some quantum information, and there are quantifiable measures for quantum information that will come to in due course when we discuss the idea of the density matrix. This quantum information has to transmit to Bob. So let me come up with a quantum circuit that achieves this. And many of the ideas that we've been discussing will come to light in this kind of argument. So Alice gets a quantum state psi. So this is Alice living here, right? This is Alice's world. G.
Is this some kind of a cloning as well? Will we have this?
Let's see. It's not cloning, because the original state is going to be destroyed. So Alice gets this quantum state psi. She gets a qubit perhaps. Now the qubit is embodied in a certain piece of matter, say an electron, spin, photon. So there is some kind of physical system that she gets, which is in the state psi. She gets some matter which is in the state psi. Now what she would like to do is, without measuring this quantum state, because if she measured the quantum state, she will never be able to tell what the quantum state is unless she has multiple copies of psi coming in, and she repeats the experiment over a large number of times, and she builds the statistics and gets the probabilities, and from the probabilities she is able to infer the probability amplitudes. And that's not a one-way process. So if I have the number 3 or number 0.5, the probability amplitude is not simply the square root of 0.5. There's a phase factor associated with it. So alpha and beta. So if you want to really measure a quantum state psi, you need to know two parameters, theta and phi. If you're dealing with a pure state. If you're dealing with a mixed state, which will come to later, you need to know more parameters. So you need to know some parameters, and it's not possible for Alice to do all of this if she doesn't have an infinite supply of qubits coming in, all prepared in the same state. Right? And the preparer does not have the liberty or the means to prepare copies of the same state. So everything is kind of a roadblock here. Alice cannot measure the state, so how can she tell Bob what state to prepare? Right? So this is the question at hand. So we're designing an algorithm, a quantum circuit that achieves this task. So Alice gets a piece of matter, electron, proton, whatever, which is in the quantum state psi. Now in order to assist the teleportation process, another pair of qubits is needed. Right? So here we have the concept of this scratch qubit here, a scratch register, or an auxiliary quantum system, or an ancillary quantum system. Normally it's the term that is used for these qubits that help in an algorithm. They are called ancillary qubits, auxiliary qubits. So two qubits are prepared, which are ancillary qubits, and the qubits that are prepared are entangled. So we prepared an entangled pair. Suppose that entangled pair is 1 over under root 2 ket 0 0 plus ket 1 1. And one of the particles in this entangled pair goes to Alice and the other goes to Bob. Bob is somewhere far away. So now you have three particles. One particle bears the quantum state psi, which is to be transmitted to Bob, and Alice gets that particle. But Alice also receives another particle, and the particle she receives is in fact a part of an entangled pair. So an entangler, some kind of circuit or some kind of preparer, is preparing entangled particles whose quantum states are entangled. Suppose this preparer is preparing this Bell state. So now this is an entangled state. Now in this scheme we now have three qubits. Let's call this qubit number 1, qubit number 2, qubit number 3. 1, 2, 3. Alice gets qubit 1 and 2, and Bob gets qubit 3. So this is really the second qubit here in our ordering. This is the third qubit. Second, third, and this initial qubit is arbitrary, alpha ket 0 plus beta ket 1. And Alice gets the first two qubits. One is the unknown qubit she wants, whose information she would like to transmit, and one is one of the entangled pairs. Now what she does is she does a quantum gate or a unitary operation on the two qubits in her possession. What she does is the following. Alright? So this is a controlled NOT gate. So let's see what sequence of events is unfolding here. Do you understand the circuit? Alright. So, G.
Is there any specific reason we're using the same symbol but in different states? We decide the first deciding or third to be उसके लिए हमने सारे these
ये तो मैंने पहले से पहले से लिख दिया, ठीक है? So now initial state is, initially our state is psi, first qubit, and the second and third qubits are in this entangled state. Right? So this is my initial state. So what I could do is I could write this as 1 over under 2. This is alpha 0 plus beta 1, and the second and third qubits are correct. So this is my initial starting state. Now let's do the first control knot. Nothing is happening really to this third qubit because it's going to bob. So in this part of the quantum algorithm, there's a control knot operation between the first and the second qubits only. So at this stage, let's call it, we do a control knot between 1 and 2. So if we were to do a control knot, 1 over under root 2 alpha 0 0 0 plus beta 1 0 1. So what's going to happen is that when the first qubit gets 0, nothing happens, and we need to do more. So alpha, let's first look at all the alphas. So alpha ket 0 0 plus alpha 0 1 1 plus beta 1 1 0 plus beta 1 0 1. Correct? Is this word? 1 1 0 plus beta 1 0 1. किधर? N पे ये वाला. So when this is a control knot operates on beta 1 1, so this second qubit is inverted. You get 1 0 1. So it's doing nothing to the third qubit. So the third qubit is this thing here. So let me, I just skipped a step, so let me do the entire step. 1 over under 2. So I'm going to rewrite the first state as alpha 0 0 0 plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1. Alright. So now I'm doing a control knot between the first and the second qubit. Nothing happens here. I get this. Nothing happens here. I get this. Here, the first qubit is ket 1. Therefore, the second qubit has to be inverted. I get this. And nothing happens to the third qubit. Here, from here I get this. Alright. Now what I would like to do, I would like to do a Hadamard gate on the first qubit. Now this is some tedious algebra here. Now I do a Hadamard gate on the first qubit. U Hadamard on the first qubit. I start from here. So after a Hadamard, I get another 1 over under root 2. So I just put a half here, alpha. So from this first ket 0, I get ket 0 plus 1, 0, 0, plus alpha 0 plus 1, 1, 1, plus beta 0 minus 1, 1, 0, plus beta 0 minus 1, 0, 1. So now can you do the algebra with me please? So 1 half alpha 0, 0 plus alpha 1, 0, 0 plus alpha 0, 1, 1 plus alpha 1, 1, 1 plus theta 0, 1, 0 minus beta 1, 1, 0 plus beta 0, 0, 1 minus beta 1, 0, 1. Got it? So far so good? Now let's do something really quite straightforward. Let's look at this term and this term. Let's combine them together. So I can write this as 1 half. So here, if you look at the two terms that I've underlined in yellow, the first qubit is in an identical state, ket 0. So I can factor out the first qubit and write this as ket 0. Now I'm reintroducing the tensor product sign just for clarity, and then I have alpha, second qubit 0, third qubit 0 with an alpha sign plus beta, sorry, I'm going to factor out the first two qubits. Correct? Because the first two qubits are common. And now what I would like to do, I would like to look at this state, which I underline in pink, and I look at this state. So plus, so the first two qubits are in an identical state, 1, 0 here, 1, 0 here, plus ket 1, 0 tensored with the third qubit being in the state alpha ket 0 minus beta ket 1. Now let's look at this state which I've underlined in blue, 0, 1, and so I will get the first two qubits are 0, 1 tensored with the third qubit in the state alpha ket 1 plus beta ket 0. Finally, the two terms that remain, ket 1, 1 tensored with alpha ket 1 minus beta ket 0. So far, so good. So now this is the quantum state. Let's call this quantum state psi, say prime. This is the quantum state over here at this point. So this quantum state is psi 1 here. You're doing no measurement as yet. But now what you would like to do is you would like to perform, Alice, who has the first 2 qubits, would like to perform a measurement on her qubits. No. This is psi prime. दूसरा कौन सा है? psi 1 कहाँ लिखा है मैंने? ये वाला? ये वाला. यहाँ पे the quantum state is this. इस region में. So this is the quantum state after all these unitary operators have passed. After the algorithm has run. This is like just like a computer program that's running, and after the different steps we have a breakout point here. So this breakout point, we would like to find out what the state is. What does the machine look like? What does the finite state machine look like? What is the state of the quantum object that we study? What's the quantum state here? And that's what the quantum state is. Now what Alice would like to do, she would like to perform a measurement. And the manner in which she performs a measurement is very similar to what we've seen before. Say, I will just now draw the measurement conceptually. How she really does the measurement depends upon what technology platform we're using, whether these are photons, electrons, neutrons, or whatever. But she tries to do a measurement, and the measurement she does is she puts these conceptual beam splitters which are able to distinguish between ket 0 and ket 1. Right? And she has these detectors over here. So she has 4 detectors. Why 4 detectors? Because this channel could be ket 0 or ket 1. This channel could be ket 0 or ket 1. So what she does is she performs a measurement on her qubits. Now let's see what kind of outputs can she get. Now here is the entire quantum state. The third qubit is in the possession of Bob. So we're doing nothing to the third qubit. But Alice is now trying to be adventurous. She has her 2 qubits which are a part of a giant quantum state psi prime, and she has the audacity or the boldness to measure her qubits by passing them through 2 beam splitters, and each beam splitter has 2 output channels. If one of the detector clicks, she says that my first qubit is ket 0 or ket 1. If she looks at the second qubit, she can declare that her qubit is ket 0 or ket 1 depending on which detector clicks. So now if you look at the quantum state that has been written here, what outputs can she get? What are her possible outputs? How many possibilities exist? That's the first question. So she's doing a coincident measurement on all 4 channels, output channels at the same time. How many outputs can she get? How many kinds of outputs can she get? 4. And what are those 4 outputs? She could get, so she could get click here, 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 click here. So she gets 4 outputs. And she labels her outputs as 0, 0, 0, 1, 1, 0, 1, 1, corresponding to which of her detector clicks. So her outputs are, Alice's outputs are 0, 0, 0, 1, 1, 0, 1, 1. This corresponds to her first qubit. This corresponds to her second qubit. Alright? So she has 4 possible outputs. And what's the probability of each output? Let's call this output, so these are binary numbers really, right? So if you look at in classical terms, how many bits are these outputs? Each is a 2-bit output. And when you have 2 bits, this is how the binary numbers are arranged in Boolean fashion. So this is, and if you convert to decimal, this is 0, 1, 2, 3. So let's call this outcome 1, outcome 2, outcome 0, outcome 1, outcome 2, and outcome 3, right? So what's the probability of an output 0? 1 by 4, which is just the modulus square of this half. So there's a probability of a quarter probability of getting this output, a quarter probability of getting this output, quarter for this, and a quarter for this. So each of these probabilities is 1 by 4. And you could also determine this from the rules of quantum mechanics. If you were to look at psi prime and project it onto the 4 possibilities that we're talking about, you'll get probability, amplitude, and the square. But for that, you need to know another concept, which is the reduced density matrix. So I'm not going to go there at the moment because you are sampling just 2 qubits out of 3. Right? So this requires some more mathematical sophistication. Anyway, so these are her outputs. So her output is a 2-bit string. Her output is a 2-bit string. So Alice's output is a 2-bit classical bit string. So it could be 0, 0, 0, 1, 1, 0, 1, 1. 2 bits. She gets 2 bits. So she gets a message, she prepares a message of 2 bits, classical bits, and she sends that message to Bob over a phone call or email, or just she shouts if Bob is nearby, 0, 0, 0, 1, that's something. So she sends out her outputs, her message. This is Alice's message of Alice. She sends those 2 bits through a classical channel to Bob. There's nothing quantum as yet. Everything is quantum here, but now she has a measurement, so she's entered the classical world, and she gets 2 classical bits as the output, and she sends those 2 bits to Bob. And she sends this message out to Bob. And this could be either of the 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. Okay? Okay? Now what Bob has also possesses a qubit G.
Is there a correspondence between these 4 terms
And
and the 4 terms?
right, so if she measures 0, 0, so just look at the first and the second qubit. If this is the state that gets measured, so this entire state collapses into one of the 4 possibilities. One is this possibility, the other is this, the third is this, the fourth is this possibility. Now, if the state collapses into this possibility, then the first qubit gets to the output channel, gets 0 on the first qubit and 0 on the second qubit. So this detector clicks and this detector clicks. If the state is collapsed into this fashion, she gets 1, 0, which means this detector clicks and this detector clicks.
What are the terms that
These terms, these belong to Bob. So he has not yet performed his measurement. So this third qubit belongs to Bob. Alice has nothing to do with this. She has no access over this qubit. Alice only has access over the first and the second qubit, and she performs a measurement here. Now what's happening here is that this single qubit, whose state is to be transported to Bob, is in Alice's possession, but she doesn't measure it alone. She rather does a measurement after a certain unitary operation on this qubit together with another qubit that is part of an entangled pair. So entanglement is necessary here. You have to generate this entangled pair. This entangled pair correlates with the first qubit. This gate is correlating the first and the second qubit because it's a correlated gate between the first channel, the first qubit and the second qubit. If you remember, when we were producing our entangler, making our entangler, the logic gate for the entangler looked like this. Right? So this took an input state, say ket 0, 0, and produced an entangled state. And then I argue that if I put this in inverse, I will get the inverse of this, which is a de-entangler, which will take this input state and convert it into this state. So that what we have over here is a de-entangler state, which takes some input state and does the de-entangling operation. This kind of gate, by the way, is called, this kind of operation is called a Bell state measurement operation. And why is it called a Bell state measurement operation? Because you feed it in with Bell states, you will get the 4 outputs that I've just mentioned. Abdullah, another homework question. Why is this a Bell state measurement operation? Alright. You get up to this point, so we have a 2-bit string, a classical 2-bit string, which is now transmitted over a classical channel to Bob. That classical channel could be radio waves, it could be an optical signal, it could be the clap open, it could be a Morse code, anything. But it's after all a classical signal. Now what Bob possesses is another qubit. Now Alice and Bob have decided on a protocol that if she transmits the classical sequence 0, 0, what does Bob have to do to his qubit so that his qubit is exactly in the same state as the state that Alice wishes to transmit? By looking at this recipe here, this quantum state here, suppose Alice transmits 0, 0. She happens to measure 0, 0 with a 25% probability. Then what is the quantum state of Bob's qubit? Bob's qubit. Bob has just one qubit. Right. So if Bob waits for the message, patiently waits for the message. When he receives the message, suppose the message turns out to be 0, 0. Then he's decided, he's made up his mind with Alice that if I were to get 0, 0, Alice tells her, and they decide mutually agreed that Bob has nothing to do to his qubit. His qubit is going to be in the same state as the state that Alice wished to transmit. Because this alpha ket 0 plus beta ket 1 is nothing but the original state. So automatically Bob's qubit will be in the state, the original state psi, which ought to be teleported.
But there's a 25%.
There's a 25% chance for this, right? But it always works because they've come up with a protocol. Let me finish the story. They've also decided, so let's then work with this. Let's now come to this possibility. Possibility number 1, outcome number 1, 0, 1. If this is so, now they have come up with a protocol that if Bob receives the classical string 0, 1, what does Bob have to do to his qubit so that the state of Bob's qubit matches the original state that was ought to be teleported in the first place? Sorry? A NOT gate, which is really a pi x, sigma x gate, a poly x gate. All right, so so Bob is doing something to his qubit, something u Bob to his qubit, depending upon the message that he receives. And that u Bob, if the message that Alice transmits is 0, 0, then u Bob is really do nothing. If Alice's message is 0, 1, then Bob has to do a NOT gate. Right? Or which is equal to a sigma x gate. Correct? If the message that Alice receives is 1, 0, Bob receives is 1, 0, this outcome 1, 0, what should Bob then do? Phase gate. A phase by pi, which is really a sigma z gate. So a phase gate where the phase is pi, which is really a sigma z gate, poly z gate. And if the output is 1, 1, this thing over here, what should Bob do? Not then phase. So a NOT gate followed by a pi phase shift gate, and you can work this out that this is really proportional to a sigma y gate, poly y gate. Proportional, G.
I think we have to apply the pi gate first.
If you don't apply it first, you just get an arbitrary phase factor here. So it's proportional. Yes?
And I think the same case you have to, in the order the way it's supposed to be exactly you do the pi gate and then the NOT gate.
So if you do it in the reverse order, don't you just get a global phase? I think that's what you get. Yes?
सर जो बॉब है वो एलिस के मैसेज का वेट करेगा, उसके अकॉर्डिंगली वो ऐसा ऑपरेशन लगाएगा ताकि इनिशियल स्टेट साइ जो एलिस के पास था वो उसके पास रिकवर हो जाए. So then we can say that state psi was teleported.
Exactly. So first of all, Bob has to wait, which means that this teleportation is not instantaneous. You cannot break the limit of the speed of light, because that classical information has to travel at the most with the speed of light. It must have a finite speed. So this information is not instantaneously transmitted. So contrary to popular science writing in which teleportation just happens instantaneously, it's not true. Superluminal communication, that is communication of information at speed faster than light, is not possible. So this classical message that has to go from Alice to Bob takes finite amount of time. It's upper bounded by the speed of light. If it's an electromagnetic signal, it's bounded by the speed of light. So Bob has to wait. Alice and Bob have already decided what the protocol is. Right? So Alice and Bob have decided the algorithm. So this is an algorithm. This is a rule of the game that has already been put in place. The third thing is that no cloning still works. Why is no cloning still operable here? Because one might argue that we have cloned the initial quantum state of psi from Alice to Bob. But why is no cloning not violated here? Because the first state has been destroyed. It's been annihilated. It's gone. Therefore, no cloning is still operable here. And Bob hasn't really measured his state, but he knows that after his transformation, after his quantum transformation, which is a quantum transformation, which is dependent on a classical bit piece of information, his state is going to be an exact replica of the original state. And if there are no errors in between in transmission, so no cloning is still holds true. The second is that this kind of communication uses a classical channel. So two classical bits are transmitted over a classical channel. Two classical bits, C bits, are transmitted over a classical channel, and an entangled pair has been shared between Alice and Bob. That entangled pair, even though it acts as an ancillary pair of qubits, is crucial for teleportation to work. So this communication, kind of communication between Alice and Bob, relies on two classical bits and one what is called an entangled bit, E bit. There are really two qubits that are entangled with one another. And the same algorithm will work, by the way, if you input any of the four Bell states. But then this table, this algorithm will change. This rule of the game will change. But it's going to be the same one-on-one kind of Bell state that you input. You just have to decide what gates to apply when you get a certain sequence of classical bits. So this is an example of quantum teleportation, an example of a quantum algorithm that is at work here. Really nice, works. So I've shown the exact sequence of quantum states as they go through this algorithm. Yes, your question? Neither of them knows what the initial state is. I mean, neither Alice nor Bob knows what the state is. They don't know alpha or beta. Neither of them knows alpha or beta, even after the entire sequence has run. But it's in front of you. Alice can get four possible outputs. 0, 0, 0, 1, 1, 0, 1, 1.
Suppose Alice synchronized 0, 0.
Mm-hmm.
So we are not like putting in gate or something. But if the initial state is not in that one, like alpha 0.
Alpha 0 and beta 1 is a totally arbitrary. Any state, any input state has to be written in this form, can be written in this form. So this is an arbitrary state, alpha 0 plus beta 1. Alpha could be anything, beta could be anything. So this state is to be teleported.
So if the state is in the form alpha 1, what is
State-
the initial state?
Doesn't matter. Alpha 1, beta 0, you're just swapping the indices alpha and beta. It doesn't matter. Everything is just consistent here. I mean, you don't need to know alpha and beta. The exact replica is transmitted. Do you have a question? Yes?
सर जो एंटेग्रल पेयर है लास्ट लेक्चर से हम बात कर सकते हैं कि एंटेग्रल पेयर का एक हाथ जब एलिस के पास जाता है तो शी डिस्कार्डेड द अदर वन.
She's not discarding the other one. The other is going to Bob. The other part of the entangled pair is going to Bob. She's not discarding it.
नहीं एलिस में तो एलिस के पास तो हाफ ही जा रहा है ना.
ठीक है.
और हाफ बॉब के पास जा रहा है. तो फॉर एलिस ये नहीं होगा कि उसने उसको डिस्कार्ड कर दिया क्यूबिट 3 को.
ठीक है. So what we're doing here is she's just looking at her two qubits. So that's why you need to have a concept called the reduced density matrix to determine what the outcomes are. So I'll explain that in the next lecture perhaps.
और सर जो साइड प्राइम हमने स्टेट ये बनाई तो वो जो हमें फिगर के अंदर शो किया हुआ है वो मतलब कि तीनों qubits के ऊपर psi prime होगी.
So this is a 3-qubit state, isn't it? It's a 3-qubit state. Correct? So this is the state of the 3-qubit system. Altogether. It's a delocalized state. It exists in two remote parts of the universe, one in Alice's world, the other in Bob's world, but still it's a 3-qubit state. And remember that Alice and Bob's qubits, they could be far apart, they could be on different planets, different parts of the earth, they still are entangled with one another. If that entanglement is, well, okay, so now let's look at it practically. An entangled pair is produced, right, at one location. We produce it in our lab. So two photons are produced that are entangled with one another. One photon goes to Alice, which is just close to that preparation kitchen. The other photon goes over an optical fiber to a remote location. That optical fiber could be 100 kilometers long, to another location, on another continent. Or it could be transmitted to a quantum satellite, and through that quantum satellite it can go to another part of the world through a network of satellites. So the second qubit is going elsewhere, and if no decoherence is taking place in this transmission process and sufficient signal is preserved, which can be done, then the two qubits of the entangled pair could be far, far apart, and they will still be entangled with one another. That's what's happening here. So when originally in the early 1990s, when quantum entanglement experiments were done with photons, the distance over which teleportation took place was just a few centimeters. But now it could be done over kilometers, hundreds of kilometers. So this is due to technological advance. All of this, of course, has to be implemented. With photons, it's easy. With other, say, NV centers or spins, it's difficult. With spins, even if you could do it over a few millimeters, that's a big achievement. So all of this has to be technologically implemented. That's why the second part of this course is about quantum technologies. Alright, so this is your first encounter with the quantum algorithm. In the next lecture, we're going to look at two more algorithms, the Deutsch algorithm, and we'll start looking at quantum Fourier transforms. And I also need to describe what the density matrix is, because that's coming over again and again. Right? Thank you.